Morning, guys and girls. Today, I want to talk to you guys about what you see up here on the screen, factors that affect the rate of dissolving. Shouldn't take very long, pretty short and sweet topic. Wanted to quick recap how we got here, all right, and then talk you through these things and then send you guys on your way for the day. So from yesterday, we went through separating things into the three types of mixtures, and you notice a lot of substances are what we would call solutions. Right? And we said that how do we create those solutions? And many solutions are created from dissolving a solid into a liquid. And we got into the idea that that term is called being soluble if you're able to be broken down. And that every solution has two fundamental components. The solvent, the thing that does the attacking, which is most often water, and the solute, the solid most often, right, that's getting broken down by the water. And the general idea was that these solvent particles, the water, use their opposite charge attraction to grab onto one of the two charged ions in an ionic compound like salt. And if enough of them can gang up on it, they can tear a piece off, right? So this chloride ion right here, 1, 2, 3, 4, 5, looked like it took 6 water molecules to bind it to tear it off. And that number varies substance to substance. All right, 1, 2, 3, 4, 5, 6 here for the sodium ion. All right, but the solute is the thing that gets broken down. The solvent is the thing that does the attacking. And then we started talking about, well, what are some things that those solutions can and can't do once they start to get broken down and look like this. And we said one of them is their ability to hold more solid or not hold more solid. And they give those names. Unsaturated is when you have enough liquid that you could dissolve more solid particles. Saturated is when all of your particles of your solvent, the water, look like this. They're all stuck to an ion, so there's no fresh ones to go in and keep binding. And then we said supersaturated is when we can convince these waters to hold more ions than they think by heating them up and then cooling them down. But usually the moment that we disturb that solution, they start releasing the extra ones that they can't hold, and you're right back to where you started with the saturated solution. We said that's all called solution equilibrium, that you can dissolve and recrystallize, and that goes back and forth at equal rates. All right, and rates is a big theme of the day, rate of dissolving. And the last thing we said is sometimes, depending on what you dissolve, you can conduct electricity. And if you are an electrolyte, you tend to be an ionic substance, you can conduct because you have ions in the solution. And if you're covalent, you can still dissolve, but you don't create the ions. You don't create these positive and negative charges. So you're dissolved, but you do not conduct because it's the ions that make you able to conduct. And then last but not least, we said there's this other category that conduct just a little bit called weak electrolytes. And those we save for later because it's most commonly done with weak acids and weak bases. All right, so like I said, today I want to talk about what can we do to make substances dissolve, disappear in water more quickly. And that's known as factors that affect your rates of dissolve. Now, the first thing I want you to understand is the three things I'm going to describe increase how fast something that's already soluble dissolves. So sugar dissolves in water naturally. I can do things to make it happen faster. What these things can't do are make something that's insoluble start to break down. For instance, if I throw a bowling ball into a beaker of water, it won't dissolve. Even if I crush it up or agitate it or heat it, I can't magically make the bowling ball dissolve. It's not naturally soluble. So these things speed up naturally soluble processes. The first one is by increasing the surface area, right? And the most common way of doing that is crushing, which is sometimes called pulverizing, all right, the solute. Here is why that helps. Right? If you look at, say, a cube of salt, right? It's the guy here in the green. We put it in a beaker of water, and we have all these waters surrounding it. So the waters, just like in the previous picture, are going to use that opposite charge attraction to start trying to grab on to these green ones. The only thing is the waters can't get at any of them except these ones on the outside. Because remember, one of our properties of a solid is that they don't diffuse very well. So the water can't get in here and wiggle its way down to the middle. It just gets the outside one, pulls one off. Gets an outside one, pulls one off. So it breaks this guy down a layer at a time. The outside layer goes like peeling an onion. Next layer goes, next layer goes, next layer goes. So what we can do is give the water more opportunities to attack the solid. And we do that by breaking it down. We increase the surface area. We take this crystal and we break it up into a bunch of littler pieces. Now, all of a sudden, the water can get at a bunch of the particles that used to be on the inside because they're in these tinier pieces. They're still on the outside of the tinier pieces, but there's way more access sites. There's way more dissolving binding sites for the water to attack, and that's exactly what happens. They're able to break these mini clusters down much faster than they're able to break the big cluster down. All right, so increasing the surface area is the first way we can speed up the rate of dissolve. All right, second way, all right, is by agitating the solution, right? And most common ways of doing that are stirring it, either with, a stir rod, a spoon. I could put a magnetic stir bar in here and put it on a magnetic plate and it could spin, or I could cap the thing and I could shake. All of these agitate the solution. Right, so why does this help us? Right, well, if you look at the picture from before, here's what the crystal starts to look like as we dissolve it. Right? We started with a full cube, but these waters have come in and ripped some pieces off. Right? What's going to happen, and what this picture doesn't show, is what happens when a lot of these pieces start to disappear. So if I bring up a picture of this, what happens is you've got your cube, which is starting to get eroded, and it's got waters surrounding it. And it's those waters that attack it. Right? But the catch is, after a little while, the waters are all holding, they're all stuck to ions that they've already dissolved. And once they are attached to ions, they can't go in and attack more. So we get kind of a protective layer around the salt crystal, where one of these waters that can dive in and attack tries to go in, but he bumps into this guy and bounces back out. This guy here tries to go in, bounces back out. This guy here dives in. Hey, he made it. He can form a binding force. This guy here dives in. He made it. He can form a binding force. Right? He bounced back out. He bounced back out. So all of a sudden, all these guys in here are blocking you, all right, from continuing to attack the crystal. So what we can do by stirring this guy is take all these particles, and when we stir it, we wash these guys to the outside. And once we eliminate those, all of a sudden, all these new waters have free access to keep diving in and binding. And that's called bringing fresh solvent to the solute. So when we stir, we're getting rid of those dissolved ions that could be blocking us and letting new waters go in and keep binding, and it makes the thing break down more quickly. So that's factor number 2. Factor number 3 is heating the substance. Heating does the same thing it always does. When we increase the temperature of a substance, it makes particles move faster. So what happens is twofold. When I start to heat this sugar-water mixture, both sets of particles move faster. Right? The solid particles in here start vibrating, and they vibrate to the point that their IFs start to get weakened because you're getting vibrations, and they break apart when you overcome the intermolecular forces. The other thing that's moving faster is the water, and the water starts to bounce off the crystal more quickly and more quickly and more quickly and more quickly. Right? And both of these things make the substance break down faster. The weakened IFs coupled with the more frequent collisions of the solvent with the solute. Right? So these 3 things will make something that wants to dissolve faster, but it won't make something that doesn't dissolve. All right, so what I want you guys to do, and this would be your homework that's coming in Parent Square, is test this at home. This is one of the few things we could actually do at home. I want you guys, if you have a salt cube or a sugar cube, to take it, put it in a glass of water, time how long it takes to disappear. Then crush up a cube, put it in a glass of water, time how long it takes to disappear. Take a sugar cube, put it in a hot glass of water, heat it up, put it in, heat up the water, not the sugar cube. Time how long it takes to disappear. Take one, put it in water, stir it, see how long it takes to disappear. And then take one and do all 3. All right, so I want you to send me 4 times. All right, I lied, 5 times. Time 1, I didn't do anything to it. Time 2, I heated it. Time 3, I crushed it. Time 4, I stirred it. In time 5, I did all 3 of them at the same time. If you don't have cubes, which I understand not everybody does, just use a good old-fashioned teaspoon of sugar or a teaspoon of salt. All right. And don't worry about the ones where you're timing the crushed up, right? You would do just the teaspoon in the regular water, teaspoon in the hot water, teaspoon where you stir it, and then teaspoon where you stir it in the hot water. All right, send me those times, and hopefully we'll confirm what these claims are making, and then I'll talk to you guys tomorrow. Hope everybody's doing well.